This is a walkthrough of problem 1 on exam 2 in module 3, which can be found on page 70 in the book, The Problem Solving Guide for Electromagnetism and Optics. Problem 1. A 60-volt power supply is hooked up across two parallel thin conducting discs of radius 20 centimeters that are 5 millimeters apart. Part A, what is the electric field between the discs? Part B, what is the magnitude of the charge on one of the discs? As always, we start with a good diagram. This one's not really to scale, but if you're going to draw a Gaussian surface, it's easier to draw it on a figure like this. Let's look at a 3D view as well, just so we know what we're looking at. We have two discs connected up to the power supply. When the power supply is connected, it sucks electrons from one side and puts them on the other side until the voltage difference across the plates is the same as the voltage difference of the power supply. Let's put some labels on here. That's 20 centimeter radius, 5 millimeters apart. Now we can think about the field in here that's created. We know the potential difference between the two plates is 60 volts. Drop 60 volts in 5 millimeters. So the field is 60 volts per 5 millimeters. That's the electric field. 60 volts per 5 millimeters, which is the same as 12 volts in 1 millimeter. If it drops 60 in 5 millimeters, it drops 12 volts every millimeter. If it drops 12 volts every millimeter over a meter, it's going to drop 12,000 volts. And a volt per meter is the same as a Newton per Coulomb. So that's part A. What's the field between the discs? For part B, we ask for the magnitude of the charge on one of the discs. One of the discs is going to be positive, one's going to be negative. The battery is not a source, the power supply is not a source of electrons. It just pumps them from one side to the other. What's the charge on one of the plates? We use Gauss's law. We put a Gaussian cylindrical sleeve around the top plate. It's a cylinder, remember, the plate's a disc. Something like that. The only part of the Gaussian sleeve that has field lines going through it is the bottom. And the bottom is a circle. So here's Gauss's law. E dot A is 4 pi kq enclosed. We know what E is. That was part A. The area of the disk is just the bottom disk. That's pi r squared. No fields going through the top part. E dot A is 4 pi kq enclosed. We have one equation and one unknown. We can solve for q enclosed. And we get 13.3 times 10 to the minus 9th coulombs, which is 13.3 nanocoulombs. In this case, Q enclosed is the charge on the disk because our cylindrical sleeve surrounds the whole disk. So the answer to the question is the charge on one of the disks is 13.3 nanocoulombs. That's problem 1.